Well, hello. Today we're going to talk about electric circuits, as I told you. Here's our equations. I guess there's a few that are missing for power and for energy that we maybe talked about, but hopefully you guys will add those. The objectives for this lesson is we want to be able to interpret and construct circuit diagrams. We want to be able to identify circuits as open or closed and deduce the potential difference across the circuit load, given the potential difference across the battery's terminals. On here, what I've given you is off to the right-hand side is a bunch of pictures, and the schematic or the picture or the symbol that's used on a schematic. For wires, we use just a straight line, and then for a resistor, we use this little zigzag, which is a little bit like lightning. For a bulb or lamp, I won't use this one to the right. Quite often I'll use this one here to the left more often than not. All it is it looks like a resistor here in the middle, and then it has a light bulb or a bulb around it. A plug-in, you'll see very seldomly. A battery, we have the positive and negative terminals. I want you to understand that the positive terminal is over here with the long line, and the negative terminal is over here with the short line. So the long side of a symbol that shows the battery is always going to be the positive. The short side is always going to be the negative. A switch, we just simply have two dots, and we have the open as it shows on top and the closed one on the bottom. And I don't think we'll talk about capacitors. A schematic diagram is a representation of a circuit that uses lines to represent wires and different symbols to represent components. So, a schematic diagram. Every electrical device has a schematic diagram. Buildings have schematic diagrams. And here's a bunch of the symbols. I guess we'll go on from there. An electrical circuit is a set of electrical components connected such that provide one or more complete paths for the movement of charges. A schematic diagram for a circuit is sometimes called a circuit diagram. So we're always going to call it schematic in here. It's different jargon. An element or group of elements in a circuit that dissipates energy is called a load. If you have a drill plugged in, then the drill is the load. If you have a toaster plugged in, then the toaster is the load because it's putting a load on the circuit. Same thing with the drill. It's putting a load on the circuit. Anything you plug in is the load because it's putting a load on the circuit. A closed circuit, we kind of talked about that in class today. That's one that has a complete path to travel. An open circuit is one that has, it's open, the circuit can't travel all the way through. So if I were to draw a schematic diagram, you have to put a little battery in there, so this would be the negative, that's the positive. And then up here at top, we put a resistor. This right now is open because right here, it's open, it's not complete. Whereas if we were to put some type of switch in there, now it is a closed circuit because the electricity can flow all the way through. Actually, it flew the other way, but we'll talk about that more later. A short circuit is a closed circuit that does not contain a load. Short circuits can be hazardous. Well, imagine that we took a wire and just placed it from here and we skipped the resistor. Maybe the resistor was representing a drill. Well, what we've done is we've shorted it out. We've given and a short is just exactly what it says. The electrons now have a short path to travel. And because they have that short path to travel, they don't have to go through the resistor. That's how they get dangerous. Sometimes those really get hot and cause fires and whatnot. Short circuits are dangerous in that extent. The source of potential difference in electrical energy is an EMF, an electromagnetic field. Any device that transforms non-electrical energy into electric energy, such as a battery or generator, is called an EMF. A battery, because it takes the chemical energy and turns it into electrical energy. A generator, because it takes kinetic energy, things that are moving, and turns that into electrical energy. If the internal resistance of a battery is neglected, the EMF equals the potential difference across the source's two terminals. A battery, for example, has some internal resistance. So even though, let's say, inside the battery, let's just use a regular battery here. Inside the battery, we might be able to say there is 1.6 volts. But there's some little bit of resistance through the wiring or the connections, and at the two terminals, we're only getting a distance of, or a voltage here, potential difference of 1.5 volts, because some of that voltage is being lost to the internal resistance, or used up by that. The terminal voltage is the potential difference across a battery's positive and negative terminals. That sometimes is going to be different. For example, in my example here in blue, the terminal voltage was 1.5 volts. That's how much voltage we could register at the terminals. The battery actually produced 1.6 volts, but 0.1 volts was lost due to this internal resistance. So that much right there, 0.1 volts was lost. Our terminal voltage was 1.5 volts. The conventional current, the terminal voltage is less than the EMF. So back to here, our EMF is the 1.6. You can't really see that now. Let's put that back in there. That's our EMF, and the 1.5 is the terminal voltage. The potential difference across the load equals the terminal voltage. That's the difference between these two. So the potential difference between the top part of this and the bottom part of this, that potential difference is 1.5 volts, and that is the terminal voltage. So really what we just went over there is a lot of vocabulary. Let's talk a little bit about schematics. I'm going to pause this here and draw up a schematic. What we have here is a circuit. All right, this is a schematic of a circuit. I need to add something right there. And let's go through and identify a few things. First of all, this right here is our, it's not going exactly how I want this to be here. It looks good right now. This is our battery. This would be the plus side. This would be the negative because this is the big line and the little line. So this is our battery. This right here would be a resistor. We'd probably denote this as R1. This right here would be a light bulb because we have the resistor looking thing and a line around it. Over here would be the switch. So that right there would be the switch. It's open at this time. Having said that, I want you to go ahead and pause this, and I want you to make a schematic that has two resistors and two light bulbs. What I forgot to say is also I wanted you to include one battery. So if you need to, go ahead and pause this and include your battery. Alright, what I'm going to do here now is show you my drawing of it. You could have many different drawings of this, but I've included on here is this is my first resistor. That's my second resistor. This is my first light bulb, but you could also call that resistor 3. We could call this second light bulb resistor 4. Having said that then, the last thing I want you to do is to make another schematic that has just one battery and three Yeah, so let's make another drawing here. Sorry, let's do the exact same thing, except let's include in it an open circuit. Okay, again, in case you haven't done it, I'm going to show you a picture here. Hopefully you've made your schematic. This right here is a schematic I made. Here this has an open, this has a switch. It's an open circuit because it's open. We have our first resistor, resistor 1. This could be called resistor 2, resistor 3, resistor 4, and then down here is my battery. Tomorrow, in class, we'll have a chance to talk about this and a few more things about circuits. I'll see you on the flip side.